Okay, so for this one, we're going to do Unit 11, Worksheet 5, Analyzing Circuits. This will be Circuit C. So for Circuit C, the very first thing that we're going to do is we're going to write down what variables that we know. As usual, the resistance of the battery will be 0. Then we just copy down the resistances across each resistor. Resistance 1 is going to be 9 ohms. Resistor 2 has a resistance of 6 ohms, 3, 10 ohms, 4, 15 ohms, and 5 ohms. We know that the voltage provided by the battery is going to be 170 volts. That is going to be step 1. Step 2, we're going to determine the equivalent resistance. However, because this one is a mixture of resistors in series and parallel, we need to redraw this circuit. So the way that I'm going to do that, I'm going to keep the same power, the same voltage really, where it's going to be 170 volts for the gain across that battery. Then we're going to move over to our resistor 1, which is still going to have that same value of 9 ohms. But now I'm going to draw it, so instead of having 3 resistors in parallel, I'm going to have one resistor that is equivalent to resistors 2 through 4 that are parallel. Going to continue my current, the path, and then I'm going to keep resistor 5 the same as well. Resistor 5 is 5 ohms. So when I have it this way, I need to determine the equivalent resistance of those 3 resistors in parallel. So the equivalent resistance of resistors in parallel, 1 over resistor 2, so 1 over 6, plus 1 over resistor 3, 1 over 10, plus 1 over resistor 4, 1 over 15. Add those together, and then take the reciprocal. So that way, when we have that, we should end up with a value of 3 ohms. So the equivalent resistance of those 3 in parallel is only 3 ohms. So when we determine the equivalent resistance of the entire circuit, all of the resistors, 1 through 5, these are going to be in series. So we just add them up. 9 ohms plus 3 ohms plus 5 ohms. That will give us 17 ohms of our resistance. Once we have that, then we can determine what the current is going to be that is flowing from the battery. So the current of the battery is equivalent to the voltage of the battery over the equivalent resistance of the circuit. We have 170 volts for the potential gain across the battery. That is divided by the equivalent resistance of 17 ohms. 170 over 17 is 10, so we have 10 amps of current flowing out of the battery. So that is going to be 10 amps for current from the battery. Now that current is going to remain the same when it is on a single path. So when we are going through resistor 1, we are going to have 10 amps of current. When we continue along that path, we'll still have 10 amps right before we enter this junction, but the second we enter that junction, we're going to break up that voltage, that current into 3 different paths. Because these are 3 different resistances, the current that flows through each resistor will be different values. Eventually, they will meet up once again at this junction where each of those currents will come back together. And then once we get down to this path once again, we're going to go back to 10 amps for our current, which means that when that current is flowing through resistor 5, it should have a current of 10 amperes. We don't know what the current is going to be flowing through resistors 2, 3, and 4. All we know right now is that those 3 currents should add up to 10 amperes. What we can move on to next is going to be talking about the voltages. Now, the voltage drop across each resistor can be determined using Ohm's law. Ohm's law, voltage is equal to current times resistance. So if we want to know the voltage drop across resistor 1, we can take the current of resistor 1 times the resistance of resistor 1. In this problem, that would be 10 amps of current times 9 ohms of resistance. So we would have a drop of 90 volts here. If we were to do the same thing for the voltage drop across resistor 5, we would end up with a drop of 50 volts. Now, if we apply Kirchhoff's voltage law to this problem, then we can see that the voltage of the battery is equivalent to the voltage drop across resistor 1 plus the voltage drop across resistor 2, or in our case, 2 through 4, plus our voltage drop across resistor 5. If we were to rearrange this, so the voltage drop that we don't know, 2 through 4, is equal to the voltage of the battery minus voltage 1 minus voltage 5, which would be 170 volts minus 90 volts minus 50 volts, which would equal 30 volts. That's going to be the drop across all of this resistor. One of the properties of resistors in parallel is that they have the same voltage drop across each path that it could take. So all of those will be 30. Once we have that, then we can rearrange Ohm's law to solve for the current flowing through any path. For example, the current flowing through path, resistor 2, that's leftmost path, will be current 2 is equal to voltage drop 2 over resistance 2, or 30 volts over 6 ohms, which will be 5 amperes. 30 over 10 is 3. 30 over 15 is 2. To check to make sure that works, add up those 3 currents for the path, 5 plus 3 plus 2, which equals 10, and that should be equal to the magnitude of the current outside of the path, which it does. We had 10 amps of current before and 10 amps of current afterwards. So that's a good indication that we ended up calculating the correct current. Now, for our power, power is equal to current times voltage. So we are just going to multiply across each row. So when we are solving for that, what we're going to end up with, we will end up with 10 times 170. That will be 1,700 watts of power that is provided by the battery in this case. Across resistor 1, 900 watts would be dissipated. Across resistor 2, 150. Across resistor 3, 90. Across resistor 4, 60. And across resistor 5, 500. This is where we check our work. If 900 plus 150 plus 90 plus 60 plus 500 equals 1,700, then that is a good indication that we have analyzed this circuit correctly, because power is the rate of energy transfer. And we know that energy is conserved. It is not created or destroyed, just transferred around. So if 1,700 watts or 1,700 joules of energy transferred every second are transferred into the system, then 1,700 joules of energy every second should be transferred out of the system if we're going to be using up all of that power, which for this circuit we should be.